Hello, this is Hunter, and we're doing content review for Chemistry 221. This is week 4 topic, writing balanced chemical equations. So, a simple balanced chemical equation can be represented any number of ways, but basically we're taking our reactants on the left side and our products on the right side, and that will always be true. Sometimes this is a synthesis reaction, as we see up here at the top. We could also do a decomposition reaction where a molecule made up of A and B decomposes into its constituent parts. So we're also going to be talking about states of matter in here. It's going to be important to label these appropriately. Are they gases? Are they liquids? Or are they solids? And in these equations, they'll all be in parentheses. We'll get some practice doing this. Basically, the important thing here is getting the number of each atom, the number of each species, to match on the left side and the right side of the equation. And this will become more important as you are setting up your own experiments and as you're figuring out how much of each thing you're going to yield or that you need to start with. So just a good skill to have practiced. This is going to be a relatively short worksheet today. So the basic order for addressing these equations: start with your polyatomic ions. That's your bicarbonates, that's your nitrates, that's your those molecules that we memorized in previous weeks. Then move on to your metals. Those are going to have variable charges. Refer to your periodic tables for those. Let me make sure I have mine pulled up while I'm thinking about it. Then move on to your nonmetals. Hydrogen and oxygen comes next, and then your diatomic elements, your chlorines, your nitrogens, your oxygens, those can be done last, and those will be the easiest to balance, as we'll see when we get into an example. So all of these, again, are in the OpenStax textbook. We're on chapter 4 today, and you can follow along live or with the recording. Let's get into it. So 5a, write a balanced molecular equation describing each of the following chemical reactions. So let's see, solid calcium carbonate is heated and decomposes to solid calcium oxide and carbon dioxide gas. So let's figure out what species we have to start with. We have calcium, we have carbonate, CO3. I'm on the wrong one already. Calcium, carbonate, calcium oxide, and carbon dioxide gas. Okay. So solid calcium carbonate. We're starting with CaCO3. We know because of the charges on this that these two balance out. Calcium has a positive 2 charge on it, and carbonate has a negative 2 charge on it, so these fit together in a 1-to-1 ratio. So solid calcium carbonate is heated and decomposes. So that's our reactant. That's all that we have. Decomposes to solid calcium oxide. Now calcium and oxygen both have charges of 2 on their own. Yes, they do. So calcium is 2 positive, oxygen is 2 negative, and so those go together 1-to-1. They're a neutral molecule. And calcium oxide and carbon dioxide gas. Cool. Okay, so each of our molecules is neutral. We've got them all on the board. Are they balanced? So let's do a little bit of accounting, and I'm going to do this in a different color so that it's easier to tell. But we can just write each species on our reactant side and on our product side and just count them up. So on the left side we have 1 calcium, we have 1 carbon, and we have 3 oxygens. On the right side we have 1 calcium, we have 1 carbon, and we have 1, 2, and 3. 2 because in CO2 there's 2 oxygens, so that's 3 total. So our left and right sides match. This chemical equation is balanced. So let's look at the next one. We have an aqueous, meaning in water, and aqueous solutions of magnesium chloride and sodium hydroxide react to produce solid magnesium hydroxide, and aqueous sodium chloride. Aqueous sodium chloride. All right. So we've got magnesium. We know we're going to have chlorine. We know we're going to have sodium. We're going to have hydroxide that has a negative charge on it. And magnesium has a +2. Okay. So I'm doing this accounting over here just to... Oop, you don't need that. Keep track of my charges should I need to. Cool. Let's take a look here. That's chlorine, not calcium. So magnesium chloride, magnesium has a +2 charge, chloride has a negative charge, so we need 2 of them to balance that out. And that is in aqueous solution. And then we have sodium hydroxide. Charges balance out, so that should be neutral. These react to produce solid magnesium hydroxide. We have a +2 charge on magnesium and a -1 charge on hydroxide, so we're going to need 2 of those. That's 2. And it's solid plus sodium chloride. Sodium chloride. Okay. Are we balanced? Let's grab our different pen, do some accounting, and find out. Cool. Magnesium, chlorine, sodium, and hydroxide, and we're literally just counting these up. Chlorine, sodium, and hydroxide. Magnesium we've got 1, chlorine we've got 2, sodium we have 1, and hydroxide we have 1. On the right side we have 1 magnesium, we have 1 chlorine, we have 1 sodium, and we have 2 hydroxide. So we notice right away, let me get my pens going here. We notice right away that we have some differences. We have a different number of chlorines, we have a different number of hydroxides. So to address those, we need to put coefficients in front of each of these reactants. Let me see. Yeah, purple's going to be a great color. So we have 2 chlorines on the left and 1 chlorine on the right. So to fix this, let's do our polyatomic ions first. So let's start with our hydroxide. So we have 2 on the right, 1 on the left. Let's go ahead and add a 2 in front of this, and that gives us 2 hydroxides on the left. It also gives us 2 sodiums, so we're going to have to come back and fix that. So we've also got 2 chlorines on the right and 1 chlorine on, 2 chlorines on the left and 1 chlorine on the right. Let's go ahead and fix that by throwing that in there. It gives us 2 chlorines, and that's going to double the number of sodiums as well. It gives us a 2 there. So now let's take a peek. We've got the same number of magnesiums on each side and the same number of chlorines, same number of sodiums, and the same number of hydroxides. This is now a balanced equation. Any questions so far? Feel free to enter it in the chat. Shoot me an email if you are watching the recording of this and have any questions. All right, question 7. Colorful fireworks often involve the decomposition of barium nitrate and potassium chlorate and the reaction of the metals magnesium, aluminum, and iron with oxygen. These achieve the different colors in combustion. So write the formulas of barium and potassium chlorate. Let's write the formulas of barium and potassium chlorate. Barium nitrate. So barium, looking at our periodic table, has a +2 charge on it. Do I need to write this down? I don't think I do. Nitrate has, come back, a negative charge on it. So we're going to need, what are we going to need? We're going to need 2 of those. I think I misunderstood the question here. Involves the decomposition of barium nitrate and potassium chlorate and the reaction of metals. Write the formulas. Okay, so it wants us to write the decomposition reaction first. I'm going to give us a little bit more room here on the right. Yeah, this will work. And we're going to decompose this, and it's going to become barium and nitrogen and oxygen. So nitrogen and oxygen exist as diatomic gases in their natural states. And so that will be notated like so. And the barium may be left behind as a solid, it looks like. So looking at this, it should be pretty apparent that this isn't perfectly balanced. We have the same number of bariums on left and right, but we're going to run into a problem with our nitrogens and our oxygens. Let's go ahead and run through it. We've got 2 nitrogens over here and 2 there, but we have, excuse me, yeah, 6 oxygens on the left and 2 oxygens on the right. To fix this, let's take a look here. I see where I went wrong. Yeah. So the barium doesn't end up all by itself. We have to have an oxide, barium oxide thrown on there. Yep, that's where I went wrong. So we have three oxygens on the right side. So this is where it gets a little bit tricky. So, taking a look at our steps, start with your polyatomic ions. We've got 2 nitrogens. We have 6 oxygens, 2 nitrogens, 3 oxygens, 1, 2, and 3. We can fix this. I want to deal with my nitrogen, my diatomic nitrogen and oxygen last. So I'm going to throw this in here first, because that's going to give me now 1, 2, 3, 4 oxygens and 2 bariums. Everything else stays the same, but now we got to go on the other side here and add a coefficient that's going to double everything else. So we've now got 2 bariums, 4 nitrogens, and 12 oxygens. It gets better. Now that we have that balanced, we can start to look at our nitrogen and oxygen and change those a little bit more easily. Changing the nitrogens is easy. We just throw a 2 in front of that to double it. Excuse me, and that gives us 4 of our nitrogens that we need. And we need to get up to 12 oxygens now. Is that right? Yes. We need to get up to 12 oxygens now. We have 4. We can just add we have 1, 2, 3, 4. Yeah. So we need to get this to 10. So we're going to multiply that by 5. Gives us 10 oxygen plus 2 over here gets us to 12. Now our equation is balanced left to right. We have 2 bariums, 4 nitrogens, and 12 oxygens total on left and right. So that's a good example of why we finish with the diatomic elements last. We need to do the same thing with potassium chloride, it looks like. So potassium, chlorine, what do we got? We got oxygens. And we've got, yeah, that should be it. So, same exercise. We're starting with solid potassium chlorate. That's going to decompose to form potassium chloride, I think that's chloride, and molecular oxygen. Cool. Let's do our accounting. We've got 1 and 1, 1 and 1, 3 and 2. So we've run into a problem. It's easy enough fix. Let's start with let's see. Well, oxygen's the only one giving us a problem. So what we need to do is find the lowest common multiple of 3 and 2, which would be 6, and that's going to help us balance our oxygens. So we multiply everything by 2 on the left side. Gets us to 6. And multiply that oxygen by 3. Gets us to 6. And because we doubled our potassium and our chlorine on the left, so too should we do on the right. And now this equation is balanced. Okay. Let's see, how bad do we want to do parts B and C of this? The decomposition of solid potassium chlorate leads to the formation of solid potassium chloride and diatomic oxygen gas. Write an equation. And we've got the decomposition of solid barium nitrate leads to the formation of solid barium oxide, diatomic nitrogen gas, and diatomic oxygen gas. Write an equation for the reaction. Same. You're just changing the number of products and reactants. Make sure you're keeping track of the charges on each of those so that you have the molecules themselves balanced properly, and then you can build your coefficients from there. It's the exact same thing we just did. So now, moving on to question 11, from the balanced molecular equations, what we've been building so far are balanced molecular equations. It's the most common, I think, way that you will look at these. Now we're going to write the complete ionic and the net ionic equations for the following. So complete ionic is going to show each of the, I was just talking about charges a moment ago, each of those charged components, those charged ions in total throughout the equation. And then the net ionic equation is just going to look at the species that change. And that will hopefully make more sense in a moment. Let's see. All right, so starting with A. We've got potassium. which has a positive charge. We've got carbon. We have oxygen, has that -2 charge. We have barium, which has +2. And we have hydroxide, which has -1. And that's a good starting point. Yeah, let's see where we can go here. Okay, so we don't really... How do we want to do that? We actually want to look at this here, which has its own 2 negative charge. And what is that? I think I may have told you last week or the week before that I didn't bother to memorize a lot of these, and I really should have. Oxalate? I don't think I would expect you to know that. Anyway, so C2O4 is its own species. It has a 2 negative charge, which we can infer because there are 2 potassiums bonded to it. So that can be your starting point there. So we're now going to write these on their own. We've got potassium. That was meant to be aqueous. We have C2O4 aqueous. That has its 2 negative. We have, these are going to get in the way. We have barium with its positive charge. And we have hydroxide with its negative charge. And we're sort of repeating ourselves on the right side. So it's important to pay attention to your states here because those that are in aqueous solution still exist in their ionized forms. So potassium and hydroxide. And that last compound exists as it is because it is a solid, it is not charged. So this is our complete ionic formula. It's not balanced yet. We still need to add coefficients to these to get the same number on right and left. So let's fix this. I think I just needed to include that because it was balanced to begin with. It was given to us as a balanced equation. So I just needed to take those coefficients that already existed and put those into the ionic equation. Okay, so that's the complete ionic. Now let's look at the net ionic. And we do this by just taking a look at what changed. Let me make sure I put my states. What changed from left to right. Our potassium looks the same. Our hydroxide, does our hydroxide look the same? Our hydroxide does look the same. I needed to put a coefficient there as well. So we can really just rule those out. We don't even need to think about them. The ones that did change, I'm going to do these in green, are barium compounds here. These all changed. So the net ionic equation, we've got our aqueous barium and aqueous carbon compound over here. And I've got those out of order, but it doesn't matter that much. And our solid over here on the right. So that is our net equation. They are balanced. No coefficients needed. We're done. Okay. Let's go ahead and do the next one. Get this out of the way. Maybe. There we go. We have lead, nitrate, hydrogen. Is that hydrogen sulfate? Sure looks like it. Those are all aqueous. Hydrogen's going to have a positive charge on it. Oh, I see. So they're... How do we want to do this? Lead has a positive, nitrate has a negative. Okay, so we can start to infer some charges here based on the stoichiometry that's already in here. If we know that nitrate has a negative charge on it, there's two of them, then the lead, the metal, must have a 2 positive charge on it. That's not always going to be consistent with these metals, so you do have to pay attention to that. You can also refer backwards, or you can deduce the charge of the metal based on the ion that is bonded to it, and since that is a neutral compound, we know that it has a positive 2 charge on it. All right. Cool. That has to be 2 negative. Cool. Okay. There we go. So each hydrogen has a positive charge on it. Fantastic. So let's get our complete ionic equation on here. You know, we have 2 of those. These are all aqueous. Our solid is going to remain as is. And then we have aqueous hydrogen again, and nitrate, aqueous nitrate. On the right. Yes. Cool. So that's our complete equation. We've balanced it based on the stoichiometry that was already given to us from the molecular equation. Now we just need to figure out what's the same, what's different from side to side. And it looks like there. That's why it looked funny. Our 2 hydrogens and our 2 nitrates exist on both sides. We can ignore them. We're left with our lead and our sulfate. And our solid lead sulfate product. This is our net ionic equation. Fantastic. All right, last one. Told you it was going to be short and sweet. We're only 30 minutes in. In a common experiment in the Gen Chem lab, magnesium metal is heated in air to produce magnesium oxide. Magnesium oxide is a white solid, but in these experiments it often looks gray due to small amounts of magnesium nitride, a compound formed as some of the magnesium reacts with nitrogen. Remember that nitrogen makes up about, I think it's 20 something, 27% of our normal atmosphere, so seems perfectly reasonable. Write a balanced equation for each reaction. So this is kind of cool, right? We've got magnesium, which has this 2+ charge. We've got oxide, or oxygen, with a 2 negative charge. And we've also got our nitrogen species, which is going to have a 3 negative charge. These molecules themselves are balanced, but we're going to look at these decomposition reactions now. So individually, solid magnesium is oxidized, it burns, with gaseous oxygen, so oxygen from the air, to form magnesium oxide. Right away we can see, doing our little accounting step, we've got 2 oxygens on the left and only 1 on the right, so we can go ahead and throw a coefficient in here to fix that. It's going to give us 2 of each. We've got to throw 1 over here as well for the magnesium. We now have a balanced equation. Let's do the same thing for our solid magnesium and gaseous nitrogen, forming magnesium nitride, magnesium 3, nitrogen 2, solid. We have 2 nitrogens on the left, and 2 on the right, but we have 3 magnesiums on the right and only 1 on the left. That should be an easy fix. We just throw a coefficient in front of the magnesium. And we should be good to go. Yeah. This color coding works for my brain, but understandably can make some people a little dizzy. So I will rewrite this in black right now to make it make a little bit more sense. And there's our magnesium oxide balanced equation, and then we have our magnesium nitride balanced equation. Cool. And that's our worksheet. Again, you can find the recordings for these and for past terms on the PSU Learning Center YouTube channel. I've created a playlist for the class so you can review all of these after the fact, to check your work, to find different strategies for working through these. I hope these are helpful. Please do send me questions or feedback if you have it. My email again is hlea@pdx.edu. Hope you all have a great weekend. See you next week.